So it's my pleasure to introduce Zhang, who's giving a seminar today. She is a professor in the Department of Marine, Earth, and Atmospheric Sciences at North Carolina. And she joined NCSU in 2003, and she was at PNNL and AER before that. She has a PhD degree in chemical and biochemical engineering from Iowa, and a BS degree in environmental engineering from Tsinghua University in China, which I visited. Very nice campus. And in 2004, Yang was a recipient of the USNSF Career Award in Atmospheric Chemistry, and she will be giving us a talk on research that's going on at NCSU.
Thank you, Dr. Lamarck. Well, it's great pleasure to be here again. I always enjoy this time of Colorado Boulder. I've been here many times in the past. And I'd like to take this opportunity to thank the ASP program that allowed my student, Zhang, she's not here yet, and also myself to collaborate with UNCAR, and that's a fun experience and for both student and myself. And what I'd like to talk about today is an overview of our air quality climate earth system modeling program at NC State. All right, so I will start with a very brief background, motivation, and then an introduction of the overall research program that I'm operating in air quality focusing lab at NC State. Then I will move into case studies and illustrating the current status and capabilities of the air quality climate and earth system model through the modeling activities on the two projects, one focused on WRF Chem 5 and over East Asia in collaboration with Pacific Northwest National Laboratory and also UCSD. And the other one is the development and application of an integrated technology-driven earth system model called ITD and ESON, and which consists of a suite of models including CSM, Chem 5, and also downscaled model WRF CMAC. This is in collaboration with Argonne and USDA. The first project is currently sponsored by USDOE. The second project is sponsored by NSF together with USDA. I will wrap it up with major challenges and future direction. Since my undergraduate study, I have been fascinated with the complexity of the atmosphere. And in this atmosphere, it consists of a number of many of species and gases, of a variety of gases, aerosols, and also clouds. They interact each other through multiple processes, including chemical, physical, transport, radiation, and climate. And this is the diagram I drew while I was a first-year graduate student with Greg Carmichael at the University of Iowa back to many years ago. And so it does illustrate the complexities of the interplate interactions of the primary emissions and secondary formations of a number of oxidants, and also their roles in playing in the secondary aerosols, and which eventually affect the cloud formation and also modulate the entire Earth system and radiation budget. And based on the latest estimation by IPCC's AR5, and the aerosol direct and indirect forcing and can offset roughly half of the warming effect caused by greenhouse gases. However, there are large uncertainties associated with the aerosol direct and indirect forcing, in particular aerosol indirect effect as compared to the estimation for greenhouse gases. So this has been the main thrust for my group in the recent years' research. And in terms of research area, we have been doing a number of research model development, application, and evaluation, and for a number of areas, and that's spanning from urban all the way to global, and covering air pollution to climate, then also expanding from atmosphere to Earth system over many years. And then the modeling tools and that we have been using and developing, improving, applying, and evaluated, and include several emission models and smoke and bias and Megan, then several meteorological models, including MN5 WRF and global WRF, and a number of offline coupled or online coupled air quality climate models such as CMAC, ChemX, and Chem5 and GeoSchem, as well as online coupled WRF-Chem and WRF-Chem5 and CSM and Chem5. And lately, we have focused on development and applications of integrated Earth system model that include CSM and also integrated technology-driven Earth system model. Then we also play a little bit with the water quality quantity model, and that's based on this WQSI and water quality supply and stress, and with carbon and biodiversity model, then ecosystem model that simulate photosynthesis and also evapotranspiration with carbon and nitrogen cycle. And finally, for the more in-depth study, and my group has been applying a number of advanced probing analysis tools to understand process governing the fate of a number of species, and such as process analysis tool, and also to study sensitivities of the model prediction to a number of parameters in the model treatment and also model input and DDM, as well as the source apportionment for ozone and also for PM. So the main thrust for my group is to utilize state-of-design model system, then continuously improve the model capability in reproducing observation, then in projecting future changes in air quality, climate, and entire Earth system, and also with the ultimate goal to provide scientific base for the policy making to mitigate adverse impact that happen in the future air quality and climate and also Earth system. And for the next remaining time, I'm going to illustrate the current model status and also capability, and using a few models. And first case, and focus on WRF-Chem5 application over East Asia. The second model system is integrated technology-driven Earth system model, which include global scale CSM Chem5 model, then the regional downscale model based on WRF-Chem. All right. So the first case here is WRF-Chem5, as I mentioned. Now in this project, and we focus on improvement of several key processes, and that is currently having limitations in the regional coupled regional climate air quality models. And those largely focus on improved representations for aerosol cloud and aerosol cloud interaction processes. In particular, as I'm showing here in this cartoon, we focus largely on new particle formations here, then aerosol activation to form CCN, and through interactions with non-convective clouds and also convective clouds, as well as through forming the ice nuclei, and that in turn affect the ice clouds. And the scientific question we'd like to address here, and first, how well can climate model represent aerosol and clouds and their effect on climate and water cycle? And the other question we are particularly interested in, what are the most influential processes for aerosol cloud precipitation feedbacks? And through addressing those questions, and the best test bed we figured is over East Asia in this region, where the pollution is very heavy and with very high concentration of aerosols, which in turn give a very stronger signal for aerosol direct and indirect forcing. And so this is in collaboration with the Pacific Northwest National Laboratory and also UCSD. At NC State, we are using a triple nested domains here, start with 36 kilometer domain, and cover most of the East Asia, then nested down at 12 kilometer 12 kilometer resolution over eastern China. Then the third layer here include 4 kilometer resolution domain, one over Beijing, which allow us to study the impact of mineral dust and interaction with aerosol activation and cloud formation. And the second test bed focused on Yangtze River and Shanghai region. And this test bed allows us to study the impact of a monsoon, interaction between monsoon and aerosol formation. Then at PNL, and they are particularly interested how would aerosol affect formation of deep convective clouds as well as the impact of a monsoon. And so they start with our test bed and at 66 kilometers, then nest it down at 4 kilometers. All right, so the coupled regional climate model we use is so-called WRF-Chem5. It was initially developed by NCAR in collaboration with Pacific Northwest National Laboratory, and by incorporating Chem5 physics package into WRF-Chem 3.41. Okay, then this modeling system is further developed in my project, and at PNL, and they largely focus on these deep convection clouds and their coupling linkage to aerosol composition and size distribution. And specifically, and they incorporated modified Zhang convective cloud schemes, and that's consider microphysics scheme, and based on this Morrison and Gitland and 2008 parameterization, then the entire scheme is linked to aerosol composition and also size distribution. Another modification PNL collaborator have done is to incorporate several mixed phase heterogeneous ice nucleation scheme, and they consider different dependence on top of the D4 MIR92, which only consider dependence of ice cloud formation as a function of supersaturation, and those consider, for example, impact of additional dust, additional surface, and some other factors. Then at the PNL, that's what they have done. Then at NC State, we focus on 3 main tasks here. And first one is the online dust emission module, which is more advanced than the D4 one. The D4 module based on SHA 2008 can only apply to the land category over Mexico, and which is not applicable for other regions in the world. Then the second focus here is new particle formation, and we incorporate several parameterization here, 2 within PBL, and 1 focus on urban area, the other focus on non-urban area, then 1 above the PBL, and that's based on the I-mediate nucleation scheme developed by Professor Yufeng Qing. And then the third effort here focus on aerosol activation scheme, and the baseline model is based on Abdul Razak again. Then in our group, we collaborate with Sano Nanas, and at the Georgia Tech, incorporating a more advanced scheme based on Fontakis Nanas 2005. Then through the years, that scheme has been updated with different treatment. I will come back to this shortly. So the new and modified treatment have been incorporated into this WRF-Chem5 to form an integrated regional coupled climate air quality system, which has been applied to East Asia testbed. What I'm showing here are the impact of microphysics in the Zhang cumulus scheme in July 2008 and during a monsoon precipitation period. And the model simulation here we have done include 2. One with considering microphysics within this cumulus cloud scheme, the other without. Then the prediction of surface precipitation are intercompare with observed precipitation and data from China merge precipitation analysis. As we can see here, by considering this microphysics, we see the model can more realistically replicate the shape and also the magnitude of this monsoon rain as compared to the results without microphysics. Then we have also evaluated in terms of performance statistics for both precipitation and also short wave and long wave radiation fluxes against CRS data. And we can see here the large under prediction for precipitation against trimming precipitation analysis data has been greatly reduced from -42% to 18%. Then in terms of radiation fluxes and the simulation without considering microphysics and overestimate this shortwave radiation by 18%, which is becomes to minus 9% under prediction. So overall, by considering microphysics, we see the improvement for reproduction of observed monsoon rain in terms of both the shape and also the intensity here, as well as radiation fluxes. Now let's take a look at the impact of aerosol. To study that, and we run another simulation by reducing the baseline emissions by 70%, so sort of mimic the clean condition called MP_clean. So again, and when we compare the spatial distribution from two sets of simulation with MP and with an MP plus clean condition, we found out under the clean conditions, this monsoon rain band is much broader as compared to the original one, and also in terms of magnitude, it's also high. This attests the impact that has been reported widely in the literature that precipitation is reduced when the aerosol loading is increased, and this is largely due to the less effective production for rain and snow, where the convective system become weakened. Now, let's take a look at the impact of both microphysics and also aerosol incorporation on the surface level and atmosphere and top of atmosphere in terms of the radiation fluxes. So what I'm showing here are the difference between two sets of simulations. One is taking the difference between MP and no MP. That shows the impact of microphysics effect on the radiation at different level. Then the other one is the difference between MP and MP clean condition, which shows the impact of aerosol. And what I'm showing here are the surface predictions and for shortwave radiation, and then also atmosphere, that's a long wave, then on top of the atmosphere, and during both daytime and also nighttime. And microphysics actually make the surface, create a surface cooling, and also the cooling, the net cooling for the top of the atmosphere, although in the atmosphere we see a slight warming, and because of trapped long wave radiation. And then if we take a look at aerosol impact here, we actually see a little bit increase and for surface forcing here, and that's a slight warming. Then at the top of the atmosphere is also small warming. So the contrast here is primarily contributed by the changes in the cloud fraction. In this case, where we see increase in the cloud fraction, where in this case, where we see decrease in the cloud fraction here. Now, in terms of the relative impact on the total net radiation flux, we see the net changes driven by microphysics effect. It's much greater than the net changes driven by aerosol effect. Now take a look at the multi-year simulation we have done during the 11 time period, 2001 to 2011. We select 6 representative years, and we applying Wolfram 5 over entire East Asia at 36 kilometers. Then we use all available surface data and also satellite data to validate the model. Then in particular, we use the API, air pollution index data from China, then specific chemical and meteorological measurement data from Japan, Hong Kong, Taiwan, and South Korea. Then we evaluate a number of species here that are monitoring and doing at those stations. What I'm showing here are normalized mean bias and also normalized mean error. So if we take a look at the metrics here, and it is generally worse as compared to the model application over continental US. This is largely driven by great uncertainties in the emissions and over Asia. And good thing is that we see some good performance for some species like ozone, and we're getting within roughly 20 15% over prediction, and EPA standard sort of like plus minus 15. That's like a good performance. And so performance is here either good or marginal. And for PM 2.5, and typically we use plus minus to judge a good performance. Then in this case, we got PM 2.5 22%, then PM 10 is 15%. So basically, it's a mixed performance, but we understand the bias-driven the factor-driven large bias here. Then by evaluating additional variables, and for example, meteorological variable and also column abundance of masses, it helps us to understand the causes for the bias here. For example, if we take a look at SO2, column SO2, we see a large overprediction here. However, the surface SO2 is all consistently underpredict. This indicated problems in the vertical allocation of the emissions. In particular, the stack height information from China are scarce, and people typically use stack height information from US, and US typically stack height and like 100 to 300 meters, but in China it's much lower than that. So we said we underestimate the emissions near at the surface, but we overestimate emission for higher altitude. Now another information here from this table is the overestimation of precipitation, which can explain in part the underprediction for PM 2.5 and PM 10. Now, if we take a look at that specific evaluation here, what I'm showing here are 5-year average ozone and measurements indicated by the blue bar, then the simulated indicated by the red bar here at 6 major cities in Japan. And then the bottom one is a similar plot, but for PM7, that's suspended PM. What we can see here, the model does a reasonably good job in capture ozone, but it underestimates PM concentration to a large extent. Then the data from China are available, but not available for research in China. But for people outside China, it's difficult to apply the data. And in our case, we collaborate with several top organization universities, and we're able to get some limited data for validation. So what I'm showing here are the comparison at 2 sites, Meiyun, and that's a remote site. Then the other one is Tsinghua, that's more like a rural site, and both are located in the Beijing, Greater Beijing area. And we can see at the Meiyun site, and PM 2.5 over predict by 10-20% here. Then at Tsinghua site, we see larger underprediction here. Now, if we take a look at composition, and in this case, and regardless whether it's a rural site, more polluted versus clean site, and we see underprediction for secondary aerosol like a sulfate ammonia. Then if we take a look at daily PM 2.5 comparison, and from the model simulation and from observation indicated by the black dot here, we see the model does a decent job in capture typical level of PM 2.5. However, it failed to reproduce a peak and during the pollution episode, heavy pollution episode. Now, in terms of the column mass, and the top panel here showing evaluation of column NO, column and ozone, and also aerosol optic depth against observations. And then the normalized beam bias are given right here. And we can see a fairly good agreement of the model predict a column abundance of NO2 and ozone. However, the model significantly underpredict aerosol optic depth. This can be explained in part with the underprediction in PM 2.5. Then the evaluation of precipitation and shortwave radiation at the ground, and also cloud droplet number concentration indicated that, and the model does a good job in reproducing precipitation, then also for shortwave radiation. However, it significantly underpredict cloud droplet number concentration, and this has to do with one bug reported by Steve Gann at the CSM workshop last week, and there was a bug in calculating maximum supersaturation, which can close the gap by 30%, but not the entire story, and I will show you more later. All right, so aerosol activation treatment, like I mentioned, we incorporate more advanced parameterization developed by Sano Nanas and based on Funkakis Nanas 2005. Then studying that, and the group has been continuously update the aggravation treatment by incorporating CCN, additional CCN based on insoluble adsorption, which is supposed generating more CCN and more cloud drop number concentration. This was published in Kuma 2009. By the way, the color code in the reference corresponds to the treatment here. Then another update is to consider this joint CCN equilibrium, which tends to slow down the condensation relative to cloud formation time scale, and this would reduce cloud droplet number concentration. And the last update is to consider entrainment effect associated with convective cloud system, which also reduce the cloud droplet number concentration. So in our case, we did simulation and with the default based on Abdul-Razak parameterization, then based on the baseline FN 2005, then one new treatment on top of the baseline at one time, then finally the combination of all the three recent updates. And based on statistic here, and we can see, for example, CDNC, we have two sets of satellite-derived observations, one from Terra and the other from Aqua. And if we take a look at Abdul-Razak baseline, we see generally minus about 60% of under prediction. Then when we use Fontokis Nanes 2005, we see much less under prediction. When we consider additional CCN resulted from insoluble adsorption of black carbon and mineral dust, and we can see less under prediction against Aqua, then under prediction changed to over prediction against Terra. Then when we consider this joint CCN equilibrium, and we see reduced the CDNC as compared to the baseline, but it is still improvement as compared to Abdul-Razak. Then similarly, this cloud entrainment also leads to less CDNC as compared to base FN 2005. But overall, when we combine everything together, and the normalized mean bias has been reduced significantly from minus 60% roughly to 2% against Terra. Then the other data set is reducing from minus 67 to minus 21, which indicated using these Fontokis Nanes series of update could lead to better model prediction for cloud droplet number concentration. Now let's move to the second case. In this case, I'm going to talk about development application of integrated technology-driven Earth system model system. All right, so the goal for this project is to estimate the impact of global change, including both climate change and land use change, on all major components in the Earth system, such as air quality, water supply, and ecosystem. And this is done by developing an integrated technology-driven Earth system model, and this is the overarching diagram for our modeling system. And start with technology-driven model that has been developed by Argonne National Laboratory, now which project the future emission changes by considering technology change and its relationship with social economic growth. Then the projected emissions will be used to drive this global and regional air quality climate simulation, and start with CSM CAN5, then downscaled with WRF-CAN. Then finally, the output from regional WRF-CAN, specifically precipitation, temperature, radiation, and also deposition parameters will be used to drive ecosystem model and also water model. And when those simulations have been validated at the large scale, we like to apply that at the local scale. And selecting California and also North Carolina having distinct meteorology and chemical emission characteristics to illustrate how the global change can change air quality, water quality, and ecosystem from all the way global to urban scale. Then the scientific questions we like to address here, and for example, how will technology policy choices affect anthropogenic emissions? and that in turn affect future Earth system. And what are the interactions among decadal climate change, air quality, water quality, and ecosystem on all the way from global to urban scale? Then what are the choices for co-benefit of climate change mitigation and air quality, water quality, ecosystem management at all the scales? And this is the schematic diagram showing how we did for this technology-driven model. And traditionally, all the project emission factors are produced by considering fuel consumptions and also emission factors, which are indicated by blue arrow here. And the new stuff in this model is the dynamic consideration of dynamic changes here, and in particular, explicitly simulate technology split in considering its relationship with social economy variables. And such a relationship is a key to understand how future technology energy use will change. And this one illustrates the mass balance for the model, where we have three types of technology change. One is the new emitters with new technology, and this is generally give lower emissions. It's a flow in. And then we have retired emitters, and those representing super emitters typically have greater emissions. They are retiring, flowing out. Then in between, and there will be some emitters and undergoing some technology update, and they still keep playing in the mass balance tool here. And so using the data from various sources like IEA and World Bank, and also growth rates from IPCC 4 scenarios, and we project the future emission, future fuel use, and future emission change under all 4 IPCC emission scenarios, then split that into on-road, off-road, shipping, and aviation, and rail. Then we also consider the relative contribution from different regions. And this is the diagram illustrates the first initial application of this dynamic technology model, and in projection how future fuel will change from 2000 all the way to 2050. Then what are the changes for emissions of CO, NOx, and hydrocarbons, as well as PM? And for the 5 years, then the 4 color line representing different emission scenarios. And in particular, and we can see under all 4 emission scenarios, and A1B, A2, B1, and B2, and we see the global consumption for fuel continuously increase. In particular, that's the case for A1B and also A2. And even with the growth of the consumption for fuel use, and we actually see a reduction for emissions for all those key species for the next 1 or 2 decades until 2030s, before they start to increase, and after 2030s. And such increase can be explained by the changes in different transport modes, and also contributions of different regions from the world. And in particular, the number 1 contributor to increase for after 2030 is the increase of the on-road emissions from Africa, and which represented by the bar here. We see substantial increases in the future years. And secondly, and we see ship emissions contribute a lot and continues to increase, and this is represented by the green bar here for NOx and also for PM. Then for CO and for hydrocarbons, and we see large contribution from non-road, which continues to increase. And the short-term decrease is largely caused by the tightening of the air quality standard worldwide. All right, so in terms of the air quality modeling, and the roadmap we take here is to first improve individual key process that affect aerosol indirect forcing. And we start with comparing emissions and considering growth factors, either from RCP scenario or from our technology-driven model. Then we focus on gas phase chemistry, aerosol microphysics, aerosol cloud interactions. We are also trying to consider dynamic land use change and in consideration both efficiency and accuracy when we improve and develop a new parameterization. Then we use Wolfram to downscale CSM global simulation. Finally, we're also in developing the interface between the atmospheric model and ecosystem model. In terms of model validation, for CSM, we have done multiple one-year test simulation. Then to evaluate the individual model representation, we implemented. Then we did 5-year simulation with prescribed SST to focus on how changes in chemical treatments cause changes in climate variables. Then this includes 5-year run with prescribed SST and also 10-year run in a coupled mode, which is used to intercompare with existing CSN CMAC5 simulation. Then for regional scale simulation with Wolfram, we have done multiple 1-month test runs, each with a different newly incorporated representation or treatments. Then for evaluation, we have done multiple 1-year simulation using boundary conditions from CSM and also MACC as part of AQMAT in the comparison. Then we are wrapping up this model development part and initial evaluation, move into the final production part. In this part, we are going to use projected emission from TDM, the model developed by Zhang, and also from RCP, then intercompare them. Then we plan to do both current year and future year simulations. Then those simulations are a pair at a global model and using CSM CAM5 with improved parameterization. Then at the regional scale using Wolfram, which is also improved also with improved parameterization, and we will do current year and future year simulations. Through the analysis, we hope to understand, quantify the global climate impact on air quality and also at the regional scale. All right, so this table summarizes the major model development and improvement activity at NC State for CSM CAM5 and also Wolf the regional scales. Then I won't go through very detailed, but in particular, the gas phase mechanism is based on CBO5. In Wolfram, we incorporate that into it, and this is one of the most popular chemical mechanisms used for regional air quality simulation. Then for global model, we expand this CBO5 to include additional reactions and in the stratosphere and also heterogeneous chemistry and also halogen reaction that are important in upper atmosphere and in particular low portion of a stratosphere that's called global extension version of CBO5. Then isotopia has been used to simulate thermodynamics for both, and the color code here, all the red, all the module and treatment in red, that's the new or modified mechanism we incorporated. Then for nucleation part, we incorporate immediate nucleation in CSM and couple that with D4 parameterization within a boundary layer and above boundary layer. Then secondary organic aerosol, we start with 1D VBS, and that include SOA forming both from SVOC and POA, then also PAH and Gliaxol. Then recently we expand that to account for gas phase functionalization and also fragmentation, and which is a key step towards 2D VBS. So we name it 1.5 VBS here. Then Wolfram, and we use existing VBS, and which only accounts for contribution from SVOC. Then there are additional modification in terms of aqueous chemistry, heterogeneous chemistry. Then finally, for aerosol activation, and on global scale, we are able to use these from Turkish Nanos 2005. Then with two updates, one considering insoluble adsorption, which tends to increase cloud droplet number concentration. The other one considering Zhang CCN equilibrium, which tends to decrease cloud droplet number concentration. So just a few snapshots from the CSM model simulation here, and I can contrast two sets of simulation, one with modification in the condensation treatment in MEM7, the other one with modification for both condensation and nucleation. The difference will tell us the impact for nucleation. And to your left, and we can see the evaluation of the two sets of simulation against the literature reported observational data largely over the ocean. Those are indicated by the circle. Then we see the normalized mean bias for the first run and it's about -13%, which seemed good. And in particular, considering the original mechanism with simple chemistry coupled with D4 MEM7, and that has normalized mean bias of above 90% of underprediction. So that's a significant improvement. However, if we take a closely, we see the model tends to overpredict the new particle formation rate over the ocean and underpredict that rate, J rate, over the land. And so this seemingly good performance results from compensation of those large bias in either direction. Then by incorporating the immediate nucleation scheme and also modify the prefactor in the empiric law, and we are getting much better performance over ocean in terms of J rate, although the overall domain-wide normalized mean bias and back to 50% of underprediction. Now, this is the one comparing the difference between those two sets of simulation, the zonal mean and spatial distribution of a column CCN and also in-cloud CDNC. And as we expected, when we use a smaller prefactor, we see reduction for both nucleation rate and also PM number concentration within PBL. Then above PBL and immediate nucleation really generates a large number of number concentration enhanced because of enhanced J rate, and which increase cloud condensation nuclei, and that will in turn increase cloud droplet number concentration. So in terms of domain-wide statistics, we see NMB underprediction has been reduced, and so is for cloud droplet number concentration underprediction, and that indicated an improvement. And this is the one contrasting a number of simulations in terms of aerosol, different aerosol activation parameterization. And the default one is based on Abdul-Razak gain. Then for FN, that's a baseline parameterization developed by Sandel-Nanes. Then FN plus KO9, that considering insoluble adsorption of black carbon and mineral dust. Then FN/B10 that consider Zhang CCN equilibrium, finally a combination of all processes. And all those are comparing with modest derived CDNC. So we can see that, and Abdul-Razak tends to underpredict this cloud droplet number concentration by 44%. When we switch to FN 2005, underprediction become overprediction by 28%. When we consider additional CCN from insoluble particles, and we see further overprediction, 30%. Then when we consider this Zhang CCN equilibrium, we actually see better performance and NMB with 10%. Finally, when we consider all the process together, NMB is 16%. Then using in situ CDNC, we can also see some differences, and the top one contrasting the simulation results and from Abdul-Razak and the baseline, and also FN series, which consider all the processes here. And FN series are indicated by the hollow circle. Then the field circle represents results from the default baseline. And the region we evaluate here include clean marine in blue and blue marine in green and continental area in red. We can see both parameterization perform very similarly in terms of two regimes, and clean marine and also polluted marine, but we see large difference for continental region. In particular, FN series does a much better job in with better agreement with in situ low-level cloud droplet number concentration. And this is the slide showing the impact of VBS SOA. And in our VBS framework, we consider two elements here. One comes from the SVOC and resulted from oxidation of anthropogenic VOC and biogenic VOC. We consider 4 volatility being here. And the other one is the photochemical aging of this primary organic aerosol, in which we consider 9 volatility beings for gases POA, then 7 volatility beings for aerosol phase POA. Then we consider both anthropogenic and biogenic agent. Now another element we recently added is based on functionalization and fragmentation. In this case, and the first the zero older, zeroth generation of the condensate product from VOC oxidation by OH, and also from the photochem region of POA are right here, and representing by 8 volatility beings. Then their first generation and second generation product are allowed to go through this functionalization process, which reduce the volatility beings, increasing SOA. Then in the third generation or higher generation product, we consider both processes, and depending on which process dominate, we could see increase or decrease in SOA. In terms of evaluation, this is the one we are showing by comparing the field camping data for secondary organic aerosol that's measured using the tracer method by US EPA, and also a number of field camping include KNX, then Ledical measurements. Then we also compare our model simulations and using VBS and D4 coupled SOA yield method coupled with CB05 global extension with the aerosol mass spectral data and provided by Professor Jose Jimenez at the University of Colorado in terms of OA, HOA, and also TOA. Finally, we use improved OC data to validate the total OC prediction. As we can see here, and the red dot here come from VBS, and the blue dot here come from the D4 aerosol yield approach. We can see a significant improvement for secondary organic aerosol with large reduction for under prediction of by 80% to 14% only when we switch from the D4 method to VBS. Then we also see large reduction for under prediction for OOA, then moderate improvement for TOA, and also organic carbon. And this is the one from 5-year simulation with prescribed SST that tells us how good the chemical aerosol improvement towards to a better agreement with the observations. What we can see here with the new representations for chemistry aerosol interaction, we see more total carbon prediction on global scale, and that leads to, of course, PM 2.5, PM 10, and that gives higher AOD, and the warm color indicated increase. Then increased CDNC and also shortwave cloud forcing. Then the evaluation statistics also indicated overall improvement and for all those variables. Then for 10-year decadal simulation in a fully coupled mode, and our target here is to validate, validate with observational data here, and also intercompare with CESM CMAC5. As we can see here, in a synoptic scale, and the two simulations with the version of CESM from my lab, then against CMAP, and give a quite similar spatial distribution for precipitation and AOD, then also most of the meteorological variables, and they perform either similarly or CESM could give a slightly better performance. But for the variable that's not available from CMAP, such as CDNC and also cloud shortwave cloud forcing, we can see the model performance from CESM and NCSU is reasonably good with 10% overprediction in the shortwave cloud forcing, and also 27% overprediction for CDNC. Now, for regional scale simulation that's driven by a global model boundary conditions, and the first test we have done is to through this ECOMAT using MACC chemical initial condition on boundary conditions. And to your left, what I'm showing here are 1-month simulations using D4 VBS module, D4 SOA SOGAN aerosol module, and also D4 VBS module, but coupled with CB05. Okay, so the observational data were collected by US EPA in July 2006 at RTP, North Carolina, and observation data here indicated in the black bar here. Then the magenta bar is the VBS simulation. Then the blue bar comes from SOGAN, which is right here, barely seeing it, which indicated, and the D4 SOGAN completely meets the SOA observation here with normalized mean bias at 99% on the prediction. By using VBS, we see this 99% on the prediction changes to over prediction 23%, largely because in the observations, they did not include all the precursors that could potentially lead to SOA, where in our model, we did include most of the precursors. Then in terms of the OC, we also see substantial improvement using VBS, although we still see on the prediction. And this, again, from VBS module within Wolfram, which does not include SOA from POA. And so POC emissions and also missing SOA could help explain the gaps here. Now, in terms of the longer-term evaluation, from April to December for 2006 at the RTP site, and we see overall it's over prediction. We overshot the observation by 75%, and the prediction still happened for organic carbon. Then at 2 sites, well, we have data from Canex, Pasadena, and so Bexware, and this is for 2010 evaluation. And we see at both sites, and even with VBS, and the model significantly underpredict both SOA and OC, indicating additional deficiency limitation that we need to work on. Then this table summarizes the overall performance for Wolfram simulations, and for we did 3 years for 10-year period, 2001, 2006, and 2010. This table summarized statistics for 2001 and 2010, a 10-year gap in between. Now, if we take a look at the statistics highlight here in red color, those are normalized mean bias in terms of percentage. Overall, the model does a reasonably good job, and in some cases, it's very good. But we do see large underprediction for aerosol optic depths, about 40-30%. Then underprediction for ocean, CCN, underprediction for some moderate underprediction for CDNC. So those also indicated some uncertainties in the model treatment in cloud microphysics and aerosol cloud interactions. Then for chain analysis, and we compare summer period in 2010 relative to summer period in 2001, trying to see how climate change and emission change affect the model prediction. And these slides showing changes in temperature at 2 meter height, and also emissions in SO2 and ammonia. And we can see in a 10-year period, and the temperature tends to increase largely over southeastern U.S., consistent with this regional climate warming. Then that leads to higher isoprene emissions and higher SOA. However, because of the emission control program enforced by US EPA, we see greater reduction for SO2. That's indicated a successful story for emission control. And with that, we see reduced SO2 and also reduced sulfate and ammonia as well. And for ammonia, there's no control yet. And so overall, it is projected. It is an increase for ammonia emission. Then because of other climate change, like reduced PBR height, we're actually seeing higher ammonia emissions. All those changes leads to a net reduction for ozone, then reduction for PM 2.5, and that also decrease availability of CCN, then decrease CDNC, then decrease AOD finally, and decrease southeastern US shortwave radiative forcing. Then this is the one showing a couple slides from our water quality model. In this case, we still use other 3 climate model because our CSM model results are not yet available. Once it's available, we are going to replace those existing climate model results. And we use 3 sets of climate models here, developed by different countries here. Then each model having 3 IPCP scenarios, A2B, A1B, and B1. Then total 9 scenarios. And the goal is to evaluate the impact of climate change on soil erosion, and which is indicated by this rainfall erosivity R. That's very sensitive to climate change. And as we can see here, and when we estimate the impact of climate change on this rainfall erosivity R for a longer time period from 1970 to 2090, we see that regardless of the model, 3 different models corresponds different color code here, then regardless of different scenarios, and 3 scenarios and noted by different symbol here, we see an overall change for this erosivity parameter R over the continental US. If we take a look at spatial distribution here, we see substantial differences. In particular, northwest and also northeast, we see higher variability in this R. The higher, that means more volatile to the erosion. And we identify the top region having the most volatility. It's in region 5. Then other top region include region 5, region 1, 2, 5, 6, and 17. Those are divided based on hydrological regions. And that corresponds to Ohio, Maryland and Indiana, Vermont and Illinois, and part of the Idaho. So those regions will have most sensitivities to the changes in the climate, which in turn change erosion vulnerability, and those are the regions the future water management should really focus on. To wrap it up here, and in the past 10 years, we have a lot of successive story, also learn a lot of lessons. And in terms of the major challenges that I've seen here, I summarize into 4 key aspects. First, the challenge is to how can we accurately reproduce air quality, climate, and their interactions. As you can see here, better model representation don't always lead to better agreement and improve the model capability. There are large uncertainties in the model treatment for new particle formation, secondary organic aerosol cloud interactions, and there are also sensitivities to both anthropogenic emission, online emission, and some boundary conditions, and then the two-way chain effect between climate variable and air quality are very complex, and sometimes it's very difficult to quantify. And for long-term simulation, we're talking about climate scale. You're talking about multi-decadal simulation. One key factor we have to consider is computational resources. So the second challenge here is how can we represent such complexities in the atmosphere and Earth system model with the computational constraints. And this is a challenge, and that's ongoing for many groups, and in particular when we consider climate change and Earth system change in a longer time scale. And there are a number of technologies available help us to characterize the bias and optimize the module, but there is a long way to go in this goal. Then the third part, we have used a lot of data for validation. And more data don't necessarily means better. And there are some conflicts and there are uncertainties for the data. So this challenge is how can we utilize existing data to help improve the model representations? How can we integrate data from different sources to reach the goal here? Then finally, and how can we link all those complex feedbacks to mitigation strategy for the entire climate Earth system model, translating the complex model results into fast decision tool that would benefit for that would lead to co-benefit for mitigation of air pollution issue and climate adverse climate change and Earth system change, and that's a big challenge. Finally, what I envision in the next several decades, the grand challenge is to how can we develop a plan, a most comprehensive integrated system model, and to attain and maintain the harmony and balance between the human and the nature, and by considering all potential stresses, including climate change, population increase, social activity, economic growth, energy, fuel, and policy decision. In particular, we have to consider 3 pillars here for sustainability, and including social and economy and environment changes here. And so this will be the grand challenge I envision for the next several decades to come. Thank you for your attention. I'd like to acknowledge all the funding agency, all the collaborators over years, and also in particular the computational resources support from NCAR-NSF, CISL Yellowstone Supercomputer, and TACC's XED Stampede, as well as DOE Hooper system. Finally, all those results are not possible without the contribution from my student and postdoc fellow. Those are the group photos over the year from 2004 and all the way to 2013. And in the middle, 2 are the team member we have, and for the Earth system project co-sponsored by NSF and also USDA in collaboration with PNL, Argonne, and USDA, involving about 20 people. Thank you for your attention. I'll be happy to address any questions you may have. No, we are running a little bit short.
So on your projections, those projections of CO, NOx emissions that you're showing over the 21st century are quite different from the RCPs, where the RCPs were just going down without rebounding. Do you know what's driving the rebound after the mid-century in the growth in the emissions that you're showing?
I mean, beyond 2050?
Yeah.
Well, we haven't done that yet. Okay.
Okay. So but it was going up. It was going back up. Maybe I don't have the dates quite right.
Well, I think it's up to, so far we projected to all the way, I think, to 2050. This is the one we had. We haven't go beyond. Yeah. So we haven't go beyond. Right here. This is
so after 20, like these.
Right. So okay. So you wonder what's the cost for that? Okay. So as I explained, there are three major contributors for increase beyond 2030. Before 2030, largely the effectiveness of emission control, that play a role. But beyond that, three major contributors. One is the large projected growth in the on-road emission from Africa, and this is right here. From Africa, you see this. This is a regional percentage contribution to the total, so they count the most as compared to others. And they don't have any standard there in force, and they have continuous demand for on-road vehicles. That's one contributor. Second contributor is the ship emissions, and to these NO, NOx, and also for PM indicated by the green bar. So this is by transport mode, the growth from 2000 to 2050, so we can see large increase for the contribution from ship. Then the third contribution, of course, it's a stable and slightly increase for on-road emissions to CO and also hydrocarbon. That's indicated for non-road emissions, indicated by the orange bar here. So those are the three major contributors predict from this dynamic technology model, and the base is different from RCP. RCP set a goal in terms of radiative forcing, and with the lowest level to highest level, 4.6 to 8.2, something like that. Then this one start with the bottom line emission projection accounting for social economic goals. So they are different projection methods. And there is one latest work trying to develop a set of projected emission that's more consistent with IPCC than the RCP right now. Yes?
I just have two questions. So you were showing organic aerosol predictions, and you were showing that when you're using POA, that helped a lot when you evaporate your POA and
that's a CSM CAN5.
Yes. So do you actually change the emissions to start with of POA, or you are just using the regular POA emissions?
Well, I think that's a good question. I think there are some papers talking about we need to adjust the emissions of POA by multiply a factor of 1.2 or 1.4 something. I think in our case, as I remember, we did adjust that a little bit and based on reported value. Right, so that's the one.
That's it, certainly. So the other question is, you're showing that with all the data that we have, we can actually get the model to agree pretty well for a lot of parameters. So do you think that we got also the right sensitivity so we can apply these models to the future and trust them? For example, NOx are going to change. Do you think that when we change the NOx today, we can reproduce, models have the right sensitivity to address these future changes?
Well, that's an excellent question. That's actually one of the motivation here for comprehensive evaluation. And when we try to improve the model representation and address all those existing known deficiency and limitation, we want to make the model better. And how can we judge the better performance? We have to use extensive data set available from all the surface network and some vertical sounding data, then satellite data for validation. So the hope is to, once that's done, and we would expect a better capability of the model we are using, then we feel more comfortable and to apply that for future projected changes. And that's the hope. Whether that's going to be done within this project period, and there are still uncertainty. As you can see, only 3 processes here we focus. It actually introduce a lot of uncertainties. Sometimes even we feel the model representations are better than the default, but the model performance are not necessarily better.
I have a couple of simple questions about the aerosol effect on precipitation in East Asia. So, first of all, what spatial resolution did you use when you showed the simulated precipitation? Is it 4 kilometer?
Well, I think for the one I'm showing, and it's a 36 kilometer.
Okay.
Then there is a plan to do 4 kilometer.
I see. So in that case, I presume that you used both convective parameterization and cloud microphysics processes in your model.
Right, both resolved cloud and also convective cloud.
And I'm wondering if you put the aerosol effect on both process or just on the cloud microphysics.
Well,
I mean, did you include aerosol effect on cloud microphysics and as well as the cumulus parameterization as well?
Right, so I think we link aerosol effect to both, see, convective clouds, and that's the one we couple through this work. Then the default, it does treat non-convective cloud interaction with aerosol.
So my final question is, which process is more sensitive to aerosol?
What are those processes?
I mean, convective parameterization versus cloud microphysics in terms of precipitation, simulated precipitation.
For this particular episode and convective precipitation, I think the impact on that is representing about 40-50% for this specific monsoon effect. So it does contribute. Then for other application we have done for larger domain, I think we're talking about 30%. So really depending on the monsoon, the time period is simulated.
But usually, in the convective precipitation, aerosol are really efficiently washed out very quickly. So I'm just wondering how, those aerosol can impact the precipitation.
How aerosol can impact precipitation?
Obviously there are two.
There are competition there, right? And one is the wet scavenging. Of course, the other one is to activate it and to form CCN. So really, it depends on the time scale and also intensity of the precipitation, right? So you could see either enhancement in the precipitation or reduction in precipitation, also depending on the size of the CCN. So in our case, we see a dominancy for the production, for the reduction for precipitation event and in the presence of aerosol. In particular, when we increase the aerosol loading from relative condition to higher, and we see that dominancy there. So you're right, and sometimes it's hard to tell, right? And whether that reduction is due to the white removing or it's due to this formation of the CCN, and that could actually shut off the warm ring formation process, slow down the cloud droplet number, concentration. Okay. All right, thank you.
Thank you, everyone. Let's thank.
Okay, thank you.